This is final presentation for DfM from Team 6, analysis and redesign of an agricultural shredder machine. An agricultural shredder is a mechanized machine that reduces crop residues and organic waste into smaller manageable pieces. The primary customers are the small and medium scale farmers, while the secondary customers are municipal solid waste handlers and community composting centers. Annual estimated demand is 650,000. Estimate production volume is 1,670,000. In the slide, right figure shows the explorer view and left table shows the list of parts in the assembly. Total part count is 20.
This fast diagram shows how the shredder achieves its main function, shred waste. The product reduces material by cutting, crushing, or tearing and then collects and contains it. To ensure reliability, it protects the mechanism and maintains stability. Convenience functions like easier access and quicker operation are included, along with features that improve user experience, such as reducing dust and noise. Overall, it shows how each supporting function contributes to the primary function.
Mapping matrix systematically maps every component to the function it contributes to, showing the complex interplay and dependencies within the machine.
On this slide, we see the product family design. There was not much change from the internal design. By observing the functions on the first diagram for our primary and secondary customer groups, 5 functions needed to be different. These were protect mechanism, reduce noise, reduce dust, contain material, and ease access. These differentiations arose due to the type of materials being shredded and the acceptable risk levels. The unique models that relate these functions were the base frame, feed hopper, and output module.
Variant and interfaces, our secondary customers are municipal party, so we had to make changes considering safety, public places, and mobility. So first, with the top bracket as common interface, we updated the feed hopper with a flap and turned output module into a collection box. Using the base frame as an interface, we added pulley protection box and caster wheels for mobility.
Here we can see the original assembly sequence and modified assembly sequence. The main difference is output module and feed hopper location have been changed to enhance delayed differentiation. Based on assembly sequence and product family assembly diagram, we have selected feed hopper and output module assembly as module part, top bracket and grate as platform parts. Reason for selection: I assembly time and I functional importance as shown in the quad chart, which is located on the left side of the slide. The right side of the slide shows the CAD before and after design. Here goes the DFA guidelines. Combining the output module and grade by removing base plate and merging the feed hopper with the top bracket, the rule DFA1 reduced part count applied while maintaining functionality. Replacing the base plate with the grade, which eliminated several fasteners, simplified assembly without affecting structural integrity, and reduced from 6 hexagonal bolts and nuts to 4 for box housing and top bracket plus feed hopper arrangement, which gives DFA2 reduced fasteners. Increased box housing part symmetry by changing location of bolts and removed slot, which is DFA6, increased part symmetry. Pre versus post DF analysis. The manual assembly time cut by 434.72 seconds, which is 49.5% faster. Efficiency increased by 4.33%. Total quantity reduced from 102 to 57. N minimum reduced from 19 to 16. Total assembly time decreased. The risk of misassembly was minimized. And material and manufacturing needs were reduced, resulting in a positive overall impact on both product function and cost efficiency.
Automated assembly, we considered total assembly as platform assembly. From the quadrant, we selected low-cost, high-functional parts and also included small, high-quantity parts from low-cost quadrant to maximize savings overall. We targeted simple, lightweight parts for automation. We excluded motor and bearing because the motor needs special handling and bearings precision fit must be done manually. Changes that we have made. So we combined bush and pulley to use DFA1 and reduce part counts. Then we use DFA6 again on pulley to increase beta symmetry by providing one more keyway at 180 degrees. The same rule we applied for mixer blades. And we also use DFA2 to reduce fasteners from 24 to 8 here. And we use DFA5. We provided hexagonal boards to reduce part variety with our other fasteners. We also reduced screws of end covers and then provided internal threading to housing and external to cover to use DFA2. Reduced 20 fastness, which enabled faster assembly and improved automation, which in design of blades, mixer blades, end cover, combined bush with pulley and could decrease theoretical mean from 6 to 5 and also improved assembly cost from 48.3 to 26.6, which is around 44.7% total improvement in automated assembly cost after applying DFA.
The plastic part selected for redesign was the integrated feed hopper and toe bracket. Machining and injection molding were the two top candidates for producing this part, but after analysis, which will be seen on the next slide, injection molding was the unequivocal choice. The parameters that determine the process were the 3D hollow shape, a mass of 1.8 kilograms, a section thickness of 7.5 millimeters, a tolerance of 0.5 millimeters, a non-critical surface roughness, and a batch size of 50,000 parts. Following these parameters, injection molding was selected as the process.
In this section, we look at the DfM analysis for the injection molded feed hopper and top bracket. The original design had two major issues. First, the wall thickness was very large and non-uniform, reaching 7.5 millimeters, which increased material usage and cooling time. And second, several phases lacked proper draft angles, making mold release more difficult. Because of this, the initial cost per part was about $14.94. When we analyzed the model using DfM Pro, it flagged exactly these problems. DFIM1 recommended reducing wall thickness, DFIM2 focused on making the thickness uniform, and DFIM3 highlighted the need for proper draft angles. After applying these changes, all walls were brought to a uniform 2 millimeters, and draft angles were added to the vertical and slope surfaces. This improved moldability, reduced ejection force, and kept all the functional dimensions intact. The impact on cost was significant. The total part cost dropped from $14.94 to $11.38, saving $3.56 per part, which is about 24% reduction. Overall, the redesign greatly improves manufacturability while maintaining product performance.
The metal part selected for redesign was the output module and integrated grate. Sheet metal forming was the unequivocal choice for this part. The analysis for this will be seen on the next slide. The parameters that determined the process were a flat sheet shape, a mass of 0.7 kilograms, a section thickness of 5 millimeters, a tolerance of 0.5 millimeters, a surface roughness of 0.8 micrometers, and a batch size of 50,000 parts. Following these parameters, sheet metal forming was the selected process.
Module fits and looks perfect, but with a cost per part calculation involving bending and holes operation comes up to $8.99. Here the initial module has 5 mm thickness and around 82 holes in total. Running through DfM Pro bugs out some DFSM followed rules, properly explained in next slide. Provided by DfM Pro, stating avoid close holes DFSM Rule 8. This feature is observed in great design and other in DFSM Rule 7 and 11 stating to avoid narrow features and avoiding bending near holes, which were in both properly followed by the 4 holes at the edges, not following the 2T rule as well. Stability as well as durability of the product. The great holes are separated by a distance of 35 mm from the center, and holes near the edges are at the distance more than the double their size, also validating the 2T rule. For other improvements, number of holes are reduced for accommodation as well as thickness is reduced for the cost reduction. It helps us to bring the cost down up to $5.719 from $8.99 cost from Hub's analytical method. Even after 20% reduction of the cost, Hub stands a little bit on the higher side. For overall, there's no negative impact on the design, and there was an improved consistency for the manufacturability of the design.
This product service system offers threading as a rental service with transport and an operator, removing the high upfront cost and maintenance burden for users. Customers get affordable, reliable threading on demand with consistent output. Environmentally, one shared threader reduces manufacturing footprint, prevents residue burning, and centralizes maintenance, making the system more cost effective and sustainable.
Design critic. Here is our design before and after. We integrated feed hopper plus top bracket, combined pulley plus bush, merged grate plus output module. Also redesigned blades and mixer blades for better symmetry, standardized all fasteners to hexagonal bolts, and increased symmetry on pulley, box housing, and blades. Improvements are: we increased manual assembly efficiency from 6.48 to 10.81, and for automated we improved efficiency by 44.7%. With DfM Pro we saved about 3.56 per injection molded part and 3.22 analytically for sheet metal part. Our pros are: there is no performance loss, parts are cheaper and easier to manufacture, and fewer fasteners that makes assembly easier. Our cons are: great hole size can be changed without redesigning the whole module, and the larger hopper may risk warpage and sink marks. Had a chance to redo, then we would make blade and mixer blade as single part, and we'll make swappable design for grade. Thank you.